Welcome to The Explainer. Today, we're going to talk about the wild lives and even wilder deaths of the universe's biggest stars. And believe me, there's a shocking connection between what happens out there in deep space and some of the most powerful weapons ever created right here on Earth. Okay, so let's just get this out of the way with a statement that might sound, well, a little ungrateful. I mean, look, our sun gives us life, right? It gives us light, warmth, everything. It's incredible. But, and I say this with all due respect, when you look at the grand cosmic scheme of things, our sun is kind of boring. So why do I say that? Well, it really all comes down to size. You see, our sun is a pretty average mid-sized star, and when it finally runs out of fuel, it's going to go out gracefully. It'll just puff away its outer layers and fade into this quiet little thing called a white dwarf. But the story for stars that are way, way more massive than our sun? Oh, that's a whole different story. It's not quiet, it's violent, it's spectacular, and it ends with the creation of a black hole.
All right, so to really get our heads around that spectacular end, we've got to look at its life first. And trust me, the life of a massive star, it's just this constant, high-stakes fight for survival. And this fight, this war, it's between two gigantic forces. You've got gravity on one side, just this relentless force trying to crush the star, pull it all inward. And on the other side, you've got this unbelievable outward push from the fiery furnace in its core, which is desperately trying to blow the whole thing apart.
So, what's the star's weapon in this fight? How does it push back against that crushing gravity? Well, it's a process called nuclear fusion. Deep down in that core, the pressure is just so insane that it literally smashes hydrogen atoms together to make helium. And when it does that, bam, it releases a massive flood of energy. That's it. That's what makes a star shine. And the science behind this incredible power plant, well, you've definitely seen it before. It's described by probably the most famous equation in all of physics, Einstein's E equals mc squared. So what does that actually mean? Well, E is energy, m is mass. Simple enough. But the real magic, the secret sauce, is that c squared part. That's the speed of light times itself. And that number is just ridiculously huge. It's a cosmic force multiplier. It means a star can take just a tiny, tiny amount of matter and convert it into a truly mind-blowing amount of energy. Now, this is where the story takes a turn. Because this amazing idea, turning matter into pure energy, it didn't just stay as some abstract science about stars. Nope. It became a blueprint. The secret of starlight didn't stay up in the sky. We brought it down to Earth, and we turned it into a weapon. And the timeline here is just staggering. Seriously, think about this. In the 1930s, a physicist named Hans Bethe is just curious. He's trying to figure out how stars work. Fast forward to 1945, and we've already dropped the first atomic bomb, which uses fission. But then, not even 10 years after that, we test the first hydrogen bomb. We literally built the engine of a star and set it off on our own planet. And the jump in power from the atomic bomb to the hydrogen bomb, it's hard to even wrap your head around it. The first A-bombs, their power was measured in kilotons. But hydrogen bombs, they're measured in megatons. That's 1,000 times stronger. To put that in perspective, it's like comparing the speed of old dial-up internet in kilobytes to modern broadband in megabytes. It's not just a little better, it's a completely different leap. Okay, but let's get back to our massive star. Because just like anything with a fuel tank, even the most powerful fusion engine eventually runs dry. And for a huge star, when that fuel runs out, well, the end is coming. And it's going to be spectacular and absolutely inevitable. So after millions of years of burning bright, the star starts to run out of hydrogen. The furnace in its core, it just sputters and dies. And all of a sudden, that outward push, the force that held the star up its entire life, it's just gone. And gravity, which has been there all along, patiently waiting, it finally takes over. The fight is over. Gravity wins. But wait, the star's core has one last desperate trick up its sleeve. It comes from the super weird world of quantum mechanics, and it's called the Pauli Exclusion Principle. Now, what does that mean? The simple way to think about it is that the universe has this rule. Atoms really, really don't like being squeezed into the same spot. They physically push back. They create their own kind of pressure.
So the big question is this quantum pushback strong enough to stop gravity? Well, back in the 1930s, a brilliant young physicist named Chandrasekhar did the math, and he found the tipping point. He figured out that if a star's core is less than about 1.5 times the mass of our sun, yeah, that atomic pressure can hold it up. But for the giants we're talking about, their cores are way heavier than that. So even this fundamental law of physics isn't enough. It can't save them. The collapse is going to happen.
And this final, lost battle against the unstoppable force of gravity, this is what creates one of the most extreme and, frankly, one of the most mind-bending objects in the entire universe.
I mean, the density that happens here is it's almost impossible to really picture. So let's try an analogy to get close. I want you to imagine taking the entire Earth, everything, every continent, every ocean, all the way down to the iron core, and squishing all of it down until it fits inside something the size of a pea. That's the kind of crazy density we're dealing with here.
So in that final, catastrophic moment, the star's core is crushed down to a single point of infinite density, a singularity. Its gravity becomes so powerful that it literally tears a hole in the fabric of space and time. It creates a gravitational well so deep that nothing, and I mean nothing, can get out, not even light. The star is gone. All that's left behind is its ghost, a black hole.
So think about this whole incredible story we just walked through. We went from the engine of a star to the most terrifying weapon on Earth to the birth of a black hole. And where did it all start? It started with astronomers just being curious. They were asking a simple, and what some people might have called a useless question. Hey, what makes stars shine? It was just basic research. And that leaves us with one last really important question to think about. What useless science happening right now? What are the things people are exploring today just out of pure curiosity that are going to completely define our world tomorrow?